Hello and welcome to this video on classification and marking. In this video I'm going to define what is meant by the term classification as far as QoS is concerned. We're going to look at how to classify layer 2 traffic, methods of classification at layer 3. I'm going to give you a brief overview of something called N-bar, and we're going to finish with something called trust boundaries. All right, so what is classification? So if you've watched any of my other videos or videos from other instructors on quality of service, you know that the first thing you have to do before you even configure anything is you, as a network engineer, have to define what traffic is important to you. In other words, what traffic you want to have special handling when there are times of congestion throughout your network. Now here's the thing, you might be able to answer that question or define that, but how does the router know that? So classification is implementing some sort of feature that translates what's in your head to what the router knows. So the first step that you have to do as the engineer is to divide your traffic into classes. And a class of traffic will receive a certain type of QoS traffic, or QoS treatment, I should say. So for example, classes might be low priority, high priority. And then you get to decide how you want your low priority traffic to be handled, and all the traffic that falls into that criteria gets handled the exact same way versus a different type of behavior that's acted upon for your high priority traffic. So what a classification feature does is it analyzes every packet that comes in and tries to differentiate it and say, okay, what criteria does this fall into? And there's many different ways of classifying traffic, and we're going to take a look at some of those. So classification features are identification features. They're not actually going to necessarily do anything to the traffic or modify it or slow it down or speed it up. Their objective is to identify it and categorize the traffic. Okay, so one of the primary things that normally goes along with a classification feature, a primary action that is typically done, is what's called marking, where once the classification feature looks at a packet and says, okay, it belongs in this category right here. That category might be low priority. That category might be voice. That category might be low latency traffic. Whatever the category is that you've defined, once the traffic is identified as belonging to that category, it's marked in some way. In other words, we apply some sort of a label or a value or a number to that traffic so that other subsequent network devices like routers, switches, and firewalls can then look at that marking and perform some action based on it. So there's three real high-level ways of classifying traffic without necessarily getting to the names of specific features. So you can classify traffic based on markings. So what this would be talking about is traffic that has already been marked by something else. So for example, let's say that traffic has already gone through your network a little bit. Some switch or router on the outer edge classified the traffic into a category like voice or video or data and applied a marking to it. Applied maybe a label giving it a number of 3 or 5 or something like that. Well, another router switch further on down the line, when it's doing classification, it could look for that number. It could look for that existing marking that was previously applied. It could be based on addressing. This is a very common way for edge devices at the edge of the network to distinguish traffic, is based on the source or destination address of where the traffic came from. Or maybe when we're talking about addressing, we're not necessarily talking about layer 2 or layer 3 addresses, but the addresses of port numbers, like the telnet port number or the HTTP port number. That would be a very common way of classifying traffic at the edge of your network. We can also do it based on application signatures. In other words, how the traffic behaves, or maybe something unique in the payload of that traffic will identify it as a certain application of traffic. So these are sort of three high-level ways that we can distinguish one type of traffic from another and put it into the categories that we've defined. So let's go through each one of these, starting with layer 2 classification. So with layer 2 classification, you really can't do that unless an Ethernet frame is being carried on an 802.1q or an older Cisco proprietary ISL trunk. So what we're looking at here with layer 2 classification is, as a frame comes in, trying to find some sort of number or value in that frame that distinguishes it as being relatively a higher or lower priority than subsequent frames that have come in before it or will come in after it. Now, if you know the structure of how an Ethernet frame is put together, you know there is no such number by default. So when your laptop or PC creates an Ethernet frame, there's no priority field in there. It doesn't exist. But if that frame is going across a VLAN trunk, like from a router to a switch or from one switch to another, VLAN trunking mechanisms like we've seen here, 802.1q and ISL, they append some additional headers to that frame. And both of them, when they append a header, there's a priority field in that header. So 802.1q is much more popular than ISL, but you can see here in both. So at the top, we've got the ISL header. And you can see that the ISL header has got a lot of fields in it, but one of those fields is a priority field. And the 802.1q tag is down below, and you can see that also has a priority field. Now, when you manipulate that priority field, when you say, oh, okay, this Ethernet frame has a priority of 2 or 3 or 1 in it, technically what we call that is class of service, or COS, as we see it right here. So if somebody says, hey, in order to classify or identify traffic in my network, I'm relying on COS to do that. What they're really saying is they're not looking at anything layer 3 and above. All they're looking at is the ISL or the 802.1q header, and they're looking for the presence of this field to identify the priority of the frame. Now, this is not used that much because these tags and headers used by ISL and 802.1q are only relevant from one switch to another. In other words, if I have switch 1 right here, switch 2 right here, and switch 3 right here, well, yes, when a frame is going across this trunk from switch 1 to switch 2, switch 1 certainly has the ability to add in this .1q tag and then to modify the user priority bits. But whatever he does with those user priority bits, that's simply for switch 2's benefit. Once switch 2 gets it, as part of his forwarding process, he's going to strip off that .1q tag, and then if he forwards it on to switch 3, the original .1q tag is no longer preserved. So if you want to do COS, that's something you have to configure on every single switch end to end because those markings are not preserved. It's stripped off on each and every switch, and then a new tag has to be applied. So for that reason, layer 2 COS is not used as much as the next one, which is layer 3 classification. Now this is probably used 85–90% of the time to classify traffic, because both IPv4 and IPv6 have built into their headers fields for prioritizing traffic. Whether or not you use those fields, they're all there already. So with IPv4, we have the type of service field right there, and with IPv6, we have the traffic class fields. Now, normally, if you don't do anything special, whenever your laptop creates an IPv4 and IPv6 packet, those fields would just be populated with all zeros, which would be basically like the default traffic. Everything is 0 by default. But you can populate those fields with other numbers to give relatively higher or lower priority to your traffic. And we're going to look at that coming up. Now, sometimes traffic, you want to categorize it based on the type of application that created that traffic. Now, if that application uses consistent TCP or UDP port numbers that are predictable, that never change, you could do it there too. You could classify the traffic based on that TCP or UDP port number. And then based on the TCP or UDP port number, you could go back and mark these fields right here. You could say, okay, if I see TCP port number 23, I know that's Telnet, so I'm going to go into my router switch and have it look for Telnet traffic, and when it sees it, I'm going to have it go into the type of service or the traffic class fields and change that from a 0 to something higher, so it gets preferential treatment. But what about some applications that don't have predictable port numbers? There are some applications that use dynamically negotiated port numbers that you can't really predict in advance. And the only way you could recognize that traffic is based on the body of the IP packet. Something about the data itself would give a clue as to what that application was. And for that, we can use something called network-based application recognition, or NBAR. So like I said, most protocols can be identified by well-known layer 3 or layer 4 numbers, but some protocols can't. They use dynamic numbers, and this is what NBAR is good for. NBAR can actually look at the data payload, and by looking for signatures, saying, okay, if the data payload has this shape and form, if it's got these particular characters inside of it, I know this particular application must have created that. Then NBAR can report back and say, here's the application, and now we can mark that traffic. Now we can go into the toss field and change it to some other number besides 0. So NBAR, as it says, supports a recognition of a large quantity of protocols. For example, like this says, one example, you could use it to match on a URL name or word or phrase within the URL. That's clearly within the payload of a packet in order to spot that. Now this is implemented by the central processing unit of a device. So while this is something you could find on routers, a lot of switches don't support NBAR as a classification mechanism. And the last thing I want to talk about in this particular video is just sort of a conceptual thing, is something called a trust boundary. Now, most host devices like your tablets, your smartphones, your laptops, your PCs, every single packet that's pumped out of that host doesn't have a marking, or they all have the same default marking of 0. But it is possible, for example, in Windows, to go into your Windows registry and change it so that packets leaving your laptop have a pre-marked field. You could go into Windows and say, hey, every packet that leaves my laptop, I want you to go into that toss byte of the IPv4 header. Instead of having it be 0, let's have it be 4 or 5. And if you do that, your hope is that the network is already configured for quality of service. It will see that number, and they'll say, oh, I'm going to give that packet preferential treatment because it's not 0, it's a higher number. But here's the thing. Do we really trust those devices? Do we trust our end user devices to mark the packets? Probably not. So we need to implement what's called QoS trust boundaries, which, like it says, is a logical point in the network. Beyond that point, we don't trust any markings. So on switches, when you enable QoS on switches at a global high-level command, by default, all the ports on that switch become untrusted from a QoS perspective. What does that mean? Well, that means that if an Ethernet frame comes in any of those ports, and that Ethernet frame is already pre-marked in some way, like it comes in and it's already got a .1Q tag with a non-zero priority, or it comes in as an IP packet and it's got a non-zero toss byte, we don't trust it. So we will set it back to 0, because we only want our network infrastructure devices marking packets and raising these numbers. We don't want the hosts doing it. So that's what a trust boundary is in QoS. It's some artificial perimeter that on the inside of the perimeter are the networking devices we have, and those are allowed to classify and mark packets. But on the outside of that perimeter, that leads to our hosts. We don't want them doing it. And if they do mark the packet, we're just going to set it back to 0 and they will have wasted their time. So that concludes this particular video. Thank you for watching.